Okay, so let us continue. Okay, there's a question: which graph is most commonly used? Is one best for theory, another practical application? Now it depends on what you are modeling. So there's nothing that is very specific. So we cannot say one type of graph is commonly used. So think about a social network. It depends on how people are connected. If everybody in the social network know each other, then it will be a complete graph. Then it could be also star graph if there's only one person who will know every other person and nobody else know each other, then that's a star graph. So it depends on the nature of the network. Okay, so a graph basically models, captures the information in your network. So it depends on what type of network you have, and there's no particular graph that's best to work on. Again, as I said, depends on the type of application or network. So there is a question: you can interchange in between directed and undirected with the same cycle. um, Really, it's not clear. So you can interchange in between directed and the same cycle. Okay, so it is like you can have a cycle where some edges are directed, some are undirected. Yes, that's possible. So yes, I did not mention it, but this question is asked. So let me mention that too. You can have what's called a hybrid graph. So a hybrid graph is nothing but a graph that has both directed and undirected edges. Again, a Twitter is a good example for a hybrid graph. So in some cases, A follows B and B will follow A also. In that case, you'll have an undirected graph between A and B because you follow each other. But most of the edges in Twitter will be directed because not everyone follows each other. But still you can have a cycle where if you can, basically a cycle is nothing but you can start from one vertex, go around and come back to a starting vertex. So that's a cycle. So let me see if we have a cycle here. Yes, so a cycle here from 0 you can go to 1, then to 2, and then come back to 0. So that's a cycle of just using these directed edges. Now if any of these edges are undirected, then you can go in both directions. So that way you can also find a cycle. Okay, now there's another question. So the complete graph would allow one to make more correlations. In a complete graph you basically have an edge between two vertices. So I'm not sure what I mean by correlation here. A correlation is nothing, is typically used to say to find out some pattern. Okay, so if there's a pattern of some edges, can we find a similar pattern in another graph? So when you want to look at a complete graph, you have an edge between any two edges. Okay, so that means the social network, everybody knows each other, so that could be the kind of correlation that you can find out. Other than that, I'm not sure what you can do to make some correlations, but the edges basically in a graph kind of capture the interaction between the entities uses here. So in a complete graph you have interaction between any two vertices can communicate. Okay, whereas in a star graph you have to always go through the hub. Okay, so if you look at from a communication point of view, if say this vertex here wants to communicate with this vertex, and the layout is a star graph, you can think about how much overhead this hub will have, because everyone has to go through this hub to communicate. So similar, think about like an airport network. So a big airport like say the Atlanta airport could be the hub to which all the smaller cities are connected. So if you want to say go from Jackson to New Orleans, right, so you cannot right away go from Jackson to New Orleans. You have to say probably go through a hub, say Atlanta. You have to go from Jackson to Atlanta and then to New Orleans. Whereas in a complete graph you can go between any two cities. So if you have like that could be the way you can think about the different type of graphs. So in a complete graph you can go from Jackson to New Orleans because there's a link between them right away. Okay, all right, so we'll move on. So we already saw this breadth first search algorithm for binary trees, and using that we really found the level numbers of the nodes in the binary tree, if you remember. Now we are going to do something similar here for a graph. The level numbers actually will represent the distance between the vertices. So even in the case of a tree, that's what the level number represents. How far is a vertex from the root node? That's the level number. Alright, so we can also find some more information about the graph by running the breadth first search algorithm. So I'm going to go through an example first, and then we'll look at the pseudo code of how to implement breadth first search, and then we'll look at some applications. Okay. So we are going to make use of a data structure called Q to store the vertices that we are visiting as part of this breadth first search algorithm. So I'll explain the use of the Q as we go through this example. So given this graph, we want to now run the breadth first search algorithm. So we'll shortly call it as BFS. So one student is telling he cannot hear. So I think everyone else can hear, right? So just check your microphone. Okay, so I assume everyone else can hear, right? Yeah, okay. All right, so we'll continue. Okay, yes, thank you. Okay, so we'll to run breadth first search, we need to have a starting vertex. Now in an exam, I need not specify a starting vertex. In that case, you could choose your own starting vertex, and we will follow the convention that the vertex with the lower ID is the starting vertex, unless you really want to start from another vertex. So here you have integers for the node ID, so we'll use the convention that the vertex with the lower ID is the starting vertex, so vertex 1. So vertex 1 is a starting vertex, and we say the starting vertex, also called the root, is said to be at level 0, because it's like distance from vertex 1 to itself, the distance is 0. And that's also the vertex that we initially put stored in the queue. So we maintain a queue and we add node 1 to the queue, the integer node ID to the queue. So so the numbers inside the circles represent the node IDs. The numbers outside the circle represent the level numbers. So to begin with, we know only the level number of node 0, and we don't know the level numbers of the other vertices, so we set them as infinity. So that's like the distance from node 1 to every other vertex. Initially we don't know that distance from node 1 to every other vertex, so we set that level number as infinity. So those are things we do as part of initialization. So we start with node 1, initialize, set up its level number as 0, set the level numbers of the other vertices as infinity, and add node 1 to the queue. Okay. So let me also go back to pseudo code so I can illustrate the same thing. So we'll start with the queue, enqueue the starting vertex, then set its level number as 0, and for every other vertex other than the source, the starting vertex, we can call it as different things. Source, starting vertex, root, everything means the same. So we'll represent as S, the alphabet for starting vertex. So everything other than the starting vertex, the level number is infinity. And we also maintain a Boolean array for every about all the vertices. Let us call it as visited, and for again all vertices other than the source, visited is false. That means have we visited that vertex as part of breadth first search. So in the initialization stage, we have just visited the starting vertex, in this case node 1. So I color the graph, the vertices, if I visit them. So in this case I color only node 1, so I have visited only node 1. The other vertices have not been yet visited, so I have not colored them. So the visited boolean will be false for the other vertices. So these are the initialization things that you do. Okay. So now we go through a sequence of iterations. Now what we do in each iteration is we dequeue the queue. So again, you know, in a queue, when you dequeue, the first entity at the head of the next to the head node will come out of the queue. So if you dequeue this queue temporarily, what will happen is node 1 will come out and the queue will become empty. That's okay. So once we dequeue, what we do is we visit the neighbors of the node that we just dequeued. So now visit the neighbors of node 1. Now the neighbors of node 1 are 2, 3 and 7. Now none of these neighbor vertices have been visited so far. So we're visiting them for the first time. So when you visit a vertex for the first time, the edge that you have to that vertex is called a tree edge. So the edge between 1 and 2 is called a tree edge. The edge between 1 and 3 is called a tree edge. The edge between 1 and 7 is called a tree edge. So you highlight that edge or make it bold and to distinguish it from some other edge you're going to see later. So this is called a tree edge now. So again, a tree edge is an edge to a vertex that you visit for the first time in the algorithm. Now, so identify those edges or classify those edges as tree edge, and as well as add those vertices, those neighbors to the queue. So the queue is empty temporarily because one was dequeued, but you're now going to enqueue, add the neighbors of 1, which are 2, 3 and 7. Now you could add them in any order. Again, we break the tie by adding them to the queue in the increasing order of their node IDs. So we add 2, 3 and 7 in this order. So 2 is the first vertex of the queue, 3 is the second vertex, 7 is the last vertex in the queue. Now we also set the level numbers of these neighbors as 1 more than the level number of the vertex from which you're visiting those vertices. So we are visiting 2 from 1. So the level number of node 2 will be 1 more than the level number of node 1. So it is going to be 0 plus 1, 1, again 0 plus 1, 1 and 0 plus 1, 1 for 7. So the level numbers of 2, 3 and 7 are each 1. So these are the things that we do in an iteration. So let us go back to pseudocode. So you run the algorithm until the queue is empty. So to begin with, the queue is not empty because it has vertex 1. So go to the inside the loop and dequeue that queue. Let u be the vertex that you dequeued. So in our example, it was node 1. Now you look at every neighbor of node u. So let us call a neighbor as node v, vertex v. If that vertex has not been yet visited, so visited of v is false, means that vertex v has not been yet visited. Like in this case, 2, 3 and 7 were not yet visited because they are not colored in this graph here. So then do these things. Increment, set the level number of node v to 1 more than the level number of node u. So level number of node u plus 1, that's the level number of node v. Mark it as been visited. So visited of v is set to true. Add that neighbor v to the queue, enqueue it to the queue, and classify the edge uv as a tree edge. So these are the 4 things we just did. Set the level number of node 2 as 1 more than level number of node 1. Similarly, level number of node 3 is 1 more than that of node 1. So for each neighbor, do that and mark those edges as tree edges, as well as color those vertices, means you have visited those vertices, as well as add those neighbors to the queue. So those are 4 things we do an iteration. So now continue to the next iteration. We again, the first thing we do is in an iteration is to dequeue the queue and look at the neighbors of the vertex that we just dequeued. So if you do that here, the queue is currently 2, 3 and 7. So if you dequeue, 2 comes out of the queue. Now if you look at the neighbors of 2, 7 has been already visited, right? So that edge that you have to 7, so the edge is like what? Is an edge to a vertex that has been already visited. So we should call this edge as what is called a cross edge. So a cross edge is an edge to a vertex that has been already visited. So If the visited of V is false, you call that edge as a tree edge. Else, you call that edge UV as a cross edge. If that vertex has been already visited, that edge to that vertex is called a cross edge. Now, vertex 4 has not been yet visited. So, and 4 is a neighbor of 2. So, you can visit node from 2. So, this edge between 2 and 4 is called a tree edge because you're visiting 4 for the first time. And we can set the level number of 4 to be 1 more than the level number of node 2. So, 1 plus 1 is 2. And mark it as a tree edge, mark it as being visited, as well as add 4 to the queue. So we have dequeued 2 from the queue. So the queue is temporarily 3 and 7. Now you add node 4 to the queue. So you're going to have 3, 7 followed by 4 as the entries to the queue. Okay. So any questions so far? Alright. So in this iteration, we dequeued node 2. So now in the third iteration, we just continue the process, dequeue the queue. So node 3 comes out. So now node 3 has 1, 4 and 5 as neighbors. But 1 and 4 are already visited. So again, this edge to 1, we already marked that edge as a tree edge. So we cannot do anything to it. But this edge to 4 has not been yet classified. So that edge to 4 should be called a cross edge because 4 is a vertex that has been already visited. Now this edge to 5 will be a tree edge because 5 has not been yet visited. So we call this edge as a tree edge and make the level number of 5 to be 1 more than the level number of 3. So it's 1 plus 1, 2 is the level number of 5, and also mark 5 has been visited and add 5 to the queue. So when you dequeue the queue, 3 comes out, so the queue is 7 and 4. Now you add 5 to the queue. Now in the next iteration, you will dequeue the queue, so 7 comes out of the queue. But all the edges attached to 7 already being classified, either tree or cross edge. So we don't have anything to do with 7. So the next iteration is just nothing. We don't do any changes to the graph. So then the next iteration, you dequeue the queue, so 4 comes out. So now you have for 4 an edge to 5, but 5 is a vertex that has been already visited. So this edge to 5 is a cross edge. That's the only thing you do for a cross edge. Now if the edge to a vertex leads to a vertex that has not been visited yet, then you have to do 4 things. What are they? Call that edge as a tree edge, say in this case 4 to 6. Then set the level number of 6 to be 1 more than the level number of node 4. So 2 plus 1, 3. Mark that vertex has been visited. Color that vertex in our case, and then also add it to the queue. So when you dequeue the queue, 4 comes out. So the queue temporarily has just 5 in it. So now you add 6 to the queue. So you have 5 and 6 now in the queue. Now the next iteration, you dequeue the queue. So 5 comes out. Now for 5, this is the only edge that has been not yet classified, and this is an edge to a vertex that is already visited. So this edge is a cross edge. So that's the only thing you can do for a cross edge. So now we're done with that iteration. Now the last iteration, just dequeue the queue. So 6 comes out, and all the neighbors and edges attached to 6 are already classified. So we don't do anything in that iteration also. So after that iteration, the queue becomes empty. So if you look at the pseudo code of the algorithm, you can do the iterations until the queue is not empty. So once the queue is empty, you come out. Okay. So that's the breadth first search algorithm. Now if you look at the time complexity of the breadth first search algorithm, again it depends on which data structure you use, whether if you use adjacency list or adjacency matrix. If you use an adjacency list, as I said, it's going to be less time consuming because you can simply traverse just the neighbors of a vertex. So from node 1, you can just go to node 2, 3 and 7 and classify the edges. Whereas if you use an adjacency matrix, you really have to go through the entire row for node 1 and see what are the neighbors of node 1, because you may think there's an edge between 1 and 5. So you have to really go through the entire row for node 1. So Now also, if you think about the number of iterations in a graph of say v vertices or n vertices, you're going to have v minus 1 or n minus 1 iterations. So that means you're going to spend v times v iteration, because for each iteration in an adjacency matrix you have to go through the entire row for that vertex that you're exploring, the neighbors. So you will have say v minus 1 neighbors in the worst case and to explore, as well as go through v minus 1 iterations. So that's why the time complexity of implementing breadth first search using an adjacency matrix is v squared. Whereas if you use an adjacency list, if you think about it, you explore these edges between 1, 2, 1, 3 and 1, 7. So these are the three edges you're looking at. And then in the next iteration, looking at just edges attached to node 2, which are 2, 7 and 2, 4. The next iteration looking at only these edges, this edge 3, 4 and 3, 5. So basically across all the iterations, you're traversing only the edges that really exist in this graph. So that is E edges. So we always indicate using alphabet E as the number of edges and V's or the vertices. So you have E edges in the graph, and you're totally looking at V vertices, looking at node 1, then looking at node 2 and node 3 and so on. So looking at V vertices and E edges. So the time complexity of implementing breadth first search using adjacency list is going to be V plus E rather than V squared. So that's why, as I said before, adjacency list based approach will give you less time, but it may be more memory intensive, whereas adjacency matrix is more time consuming, but it could be less memory intensive to store the information, if you store especially as a binary matrix. Okay, so any question? All right, so there are a lot of applications of breadth first search. So one application before we look at bipartite graph is this. Now if you start breadth first search from one vertex and you can reach all the vertices, like in this case, you can do it as a practice. If you start from vertex 1, you can go to 2, 3 and 7, and from vertex 2 you can go to 8 and 4 and so on. We'll do another example in detail, but basically you can start from one vertex and go to all the vertices in the graph. Basically you can reach all the vertices in the graph. Then we can say the whole graph is connected, means all the vertices in the graph are reachable to each other, like this. Okay. Or on the other hand, if you start breadth first search from vertex 1 in this graph, you can reach only these 6 vertices, right? Because from 1 you can go 2 and 3, and then from 2 you can go to 4, and then from 3 you can go to 5, and either from 2 or 5 you can go to 6. So, 4 or 5 you can go to 6. So if you start from node 1, you can reach only these 6 vertices. Whatever you do, you cannot reach the other 2 vertices 7 and 8. So essentially your queue will become empty before you really visit all the vertices. So that is how you decide whether the graph is connected or not, because in this case we can say these 8 vertices are still one graph, but this is not a connected graph. So why is not a connected graph? Because you really cannot run just one instance of breadth first search from node 1 and reach all the vertices. If you run breadth first search from node 1, you can reach only these 6 vertices, not the other 2 vertices. So you really have to run again another instance of breadth first search. Means you have to again start breadth first search from a new vertex, say node 7, and then reach node 8. So we can say if a graph is not connected, it has more than one component. A component is nothing but the set of vertices that are reachable to each other. So in this case we can say 1, 2, 3, 4, 5, 6. These 6 vertices form one component, whereas 7 and 8 form another component because they are reachable to each other. So we say this graph has 2 components, whereas this graph is said to have only one component. So if all the vertices are reachable to each other like this, so this is a connected graph. So a connected graph has only one component, whereas if a graph is not connected, it has more than one component. So that's one application of breadth first search. By just running breadth first search and looking at what vertices are reachable, we can find what vertices form a component. If all the vertices are forming or part of the same component, then it means the graph is a connected graph. The whole graph is connected. If only a subset of the vertices are part of a component, then the graph has more than one component. So that graph is not connected if the graph has more than one component. Okay, so that's one application. Now there's another application of breadth first search which is called a bipartite graph. We'll just look at what it means and then we'll look at an example if we have time. Okay, so a bipartite graph is like this. So you can partition the vertices to two subsets. So here you have 8 vertices, and just for it looks like there are 4 vertices in one partition and 4 in the other partition. It need not be the case. It could be 2 in one partition and 6 in the other partition. The main criteria is this for a bipartite graph. All the edges in the graph should be across the two partitions or two sets. There's no edge between vertices in the same set. So in this case, there's no edge between 1 and 4, or no edge between say 5 and 8, or no edge between say 3 and 2, or 3 and 6, or 6 and 7. All the edges in the graph are between say a vertex in this set and a vertex in this set. So we can call a set as a partition. So a bipartite graph is a graph in which we can partition the vertices into two sets of vertices. Again, two disjoint sets means one vertex here should not be in the other set. So each vertex can appear only in one of the two partitions. So and all the edges in the graph are between a vertex in one partition to a vertex in the other partition. No edge exists between vertices in the same partition. So if a graph satisfies this, then the graph is called a bipartite graph. And breadth first search can be used to decide whether a given graph is bipartite or not. So let us go through that example we just did. Or it's better to do an example where there's a bipartite graph. Let me just check if we have time. Okay, we can start with this example. We'll come back to this. So we start with node 1. Then what we do? Okay, since we don't have time, let me just sell the end result today. Next class we'll come and run the algorithm and go through the same example. But let me just tell you today how to decide whether a graph is bipartite or not. So the rule is very simple. So you start with the graph, go through breadth first search, which we'll go through next class. But after we go through breadth first search, you know that we would have classified the edges as tree edges and cross edges, and we would have identified the level numbers of the vertices, right? So you can do this as a practice and we'll come back and do it next class. Now, how to decide the graph is bipartite or not? So this is the rule. If there are no cross edges between vertices at the same level, then the graph is bipartite. So let's apply this rule here. There are cross edges, but look at those cross edges. Each cross edge is between vertices at different level. So this cross edge is between two vertices at levels say what, 1 and 2. Those are the level numbers. This cross edge is between vertices at level 1 and 2, and this is between 2 and 3. So there's no cross edge between vertices at the same level. So if a graph satisfies this property, then the graph can be called a bipartite graph. Now what are the two partitions then? The vertices in the odd level will be in one partition and the vertices in the even level will be in the other partition. So in this case, the vertices in the odd level, say odd numbers, so 1 and 3 are the odd level numbers here. So vertices 7, 3, 2 and 6. 7, 3, 2, 6. So these are the odd level vertices. So they are in one partition. The even level vertices, even numbers, 0 and 2. So vertices 1, 5, 8 and 4. So these four vertices are with the even level numbers, so they are in the other partition. And all the edges, so you can draw the same graph like this. So these are all the edges. So one between, from 1 you have an edge to 2, 3 and 7. So 1 you have an edge to 2, from 1 you have an edge to 3, from 1 you have an edge to 7. From 2 you have an edge to 4 and 8 as well as to 1. So from 2 you have an edge to 4, and from 2 you have an edge to 8 as well as from 2 you have an edge to 1. So all the edges in the given graph are between vertices in the two partitions. There is no edge between vertices in the same partition. So that's the bipartite graph. On the other hand, this is the example we just went through. If you look at the graph, the end result of breadth first search has the multiple cross edges. Now at least one cross edge you see here is between vertices at the same level. So this cross edge is between two vertices at the same level, number 1. That will rule out this graph from being called bipartite. So even if there's one cross edge between vertices at the same level, then the graph cannot be called bipartite. Okay, so go back to these two examples, work out the breadth first search for practice. We'll come back and look at the bipartite graph property one more time next class. Okay, so we'll stop with this.